Okay, for the second order system, the transfer function of second order system, in general, again, we have a second order differential equation. And if we derive the transfer function of that second order differential equation, so let's say we have a, this is our differential equation. We have e2, the second derivative, because it's a second order. Then let's say c is our output, dt squared. Then we have a1 first derivative of the output with respect to time. Then we have the constant, or we have the output. Then this is equal to the input r's of t. So in this case, this is our differential equation. We can also rewrite this. If you look at other references, they used, instead of writing the second order, they use the double dot notation. So if you experience, so these equations, this means this is a second order derivative. A1 c dot is equal to r's of t. Some also uses prime, c double prime. It means second order derivative, all the same. So let's say this is our general form for a second order. So to determine the transfer function of the second order system, we take the Laplace. And before we do that, because this is a second order derivative, and we have also a first order first derivative here. Let us first define the initial conditions. So let's say our initial conditions, c prime of 0, this is equal to 0. There's no initial condition, and also the c's of 0, to simplify our solution in solving for the transfer function. So now, taking the Laplace, the first term here, we have a2, the Laplace of a second order, s raised to n. N is the order of the derivative. This is a second order, so this is s squared. Then you multiply it with that capital letter now in the s domain. So if we have initial condition, we need to subtract those initial condition, s times c prime 0 and minus c's of 0, and so on. But because they are 0, then let's just remove them all. Then plus, for the second term, we have a1, the degree is 1. Then we have c's of s. Then plus, they just do the transformation. Then r in the s domain. This is now in s domain. So if you want to determine the transfer function, transfer function is output over the input. Remember, c is our, we designate c as our output, while r is our input. Some references also uses different variables. They use x and y, so on. But because I use c and r as the output and input of a transfer function in the introduction, then we will be using c and r. But it can be any variable. So rearranging this equation, so factor out c's of s. This is capital letter because this is now in the s domain. So we have a2 s squared plus a1 times s plus a sub 0. Then this is equal to the output or input r sub s. Then output over input, so we have our transfer function now will be equal to that output over input, and this is equal to 1 all over a2 s squared plus a1 times s plus a0. But this is not in standard form. Just like what we did in the first order system, we make the highest degree s, the coefficient should be equal to 1. So to do that, we need to multiply this with 1 over a of 2. If we multiply it at the denominator, you need to multiply it again at the numerator, so that we just multiply it by 1. And the transfer function now will become 1 over a of 2 all over s squared plus a1 times 1 over a2 all over a2 s plus a's of 0. So this is now our transfer function of a second order system. And there's some terms that we need to define for a second order. Just like in the previous, the zero order, we have the static gain, k. So we need to define them here. The general form, or standard form for a transfer function, we have just like this one, k omega n squared all over s squared plus 2 zeta omega n times s plus omega n squared. So what are these terms, new terms that I wrote here? Where k, this is what we call the static gain, just like before, static gain or static sensitivity and so on, static gain. Then we have other two parameters that we need to consider. We have omega n. This is what we call the natural frequency. Natural frequency. And the other one, zeta. This is what we call the damping ratio or damping coefficient. Damping ratio. And if we want to solve for these three parameters without doing taking the Laplace, you're given this differential equation. We can derive that from this figure, these two equation here. Obviously, k omega n squared by inspection should be equal to 1 over a2. So k omega n squared should be equal to 1 over a2 because this is the same equation, g of s. So by inspection, the numerator should be the same as the numerator of the other, also for the denominator. Then, so if you want to solve for these factors k omega n, but before that, we need to know the other factors here. So the first one that we can directly solve is the omega n squared and a 0. So from that, omega n squared is just equal to a of 0. So if we solve for omega n, this is just equal to the square root of a of 0. And if you know that, we can go back here. We can solve for k, the static gain of the system, by substituting omega n, which is a squared of a 0. So this is just a 0 equals 1 over, this is a2. a2. So solving for k is just equal to 1 over a0 times a2. There's a correction. This should be, I did multiply 1 over a of 2 here, but I did not multiply it with a0. I forgot to multiply it here. This should be a0 over a2. That's why the answer here, that is square root of a0, this should be a0 over square root of 2. So this should be a0 over a2. And this will be the square root of a0 over a2. And this should be wrong because our omega n squared will be a of 0 all over a of 2. Then if we solve this, a of 2 will cancel out, and we have 1 over a of 0. This will be the formula for the gain, and this will be the formula for the natural frequency. So if you are given this differential equation and the problem asks determine the natural frequency of this system, then without doing Laplace, you can directly determine the value for the natural frequency by knowing the coefficients of these terms, a2, a1, and a0. And it's just equal to the coefficient, a0 is the coefficient of the term that has no derivative. You divide it with a2, the coefficient of the second order derivative, then that will be your square, take the square root, and that will be your omega n, or the natural frequency. And for the static gain, it's just equal to 1 over a0. Just like before, in the first order and second order, or zero order, if you remember, here, the first order system. So here, our k should be 1 over a0. This is our k, the static gain. Here we have b over a of 0, where b is just the coefficient of r, and in the second order and first order, we make that equal to 1. So if you remove b, and this will be equal to 1 over a of 0. So the constant, the static gain are all the same for first zero order, for the first order, and for the second order system. And lastly, for the damping ratio, zeta, you look at this again. So this term, A1 over A2, should be equal to this one. So 2 zeta omega n, this is the coefficient of S here. So it should be equal to the coefficient of S at the other equation. This is equal to A1 over A2. So A1 over A2 here. Then we already know omega n is equal to the square root of that. And we can now solve for zeta, or the damping ratio. And this will be equal to A1 over 2 times omega n times A2. But what is omega n? Omega n is equal to, so this is A1, the square root of A0 over A2, multiply that with A2. So if you simplify this further, you can put A2 inside the square root. So it will become A2 squared, A2 squared, and it will cancel out the A2 at the denominator. So it's just A2 times A0. So now we can say that zeta is equal to A1 all over twice the product of A0 times A2. So this is now a formula again for the damping ratio given the coefficients of the differential equation. Now I will explain more about what are this K, omega n, zeta later on in the time response topic, because as of now, we're just doing transfer function. So the definition of these different terms will be more specifically defined later on. So this is second order transfer function of a second order system.